And we can start the English version of workshop number 2. We'll try to provide all of the workshops in English, but I sadly can't guarantee it, especially with the next one that will be with teams with previous experience, with teams from previous years, because some of those that we want to invite might not really speak English. So I'll let you know about that. But this one is really crucial in terms of completing the whole competition. So that's why it's also in English. As I said, this workshop is focused on software called OpenRocket and how to work with it. And more in general, it's focused also on how to design your own rocket if you've never done that before. I know that we have here some groups that know very well how to design a rocket, but maybe not all of you. First thing first, we have something that we promised you to tell you about, and that's the engine choice. We finished the choice, and I can proudly announce that we have a new engine for this competition that will be in use. It's called Gragas. Here you can see the main parameters. You can also find these in a new rural handbook that I've sent to Discord, and that we will also send through email. If you know the parameters of the old engine, for example, you saw them somewhere, this engine is a little bit shorter. It's a little bit has a bigger diameter. What's the important thing is that the impulse stayed almost the same at 145 Newton seconds. So in terms of apogee reached, the rockets should be really similar to last year's. And the big difference is that thanks to being bigger diameter, we have smaller overall thrust, but the engine burns for longer. Here are technical drawings of that engine. You can find all of these in the handbook. In terms of the main parts of the engine and how it works, there's the main body tube, inside which is the rocket fuel. There's a nozzle, and then there's this part. That's something that you should be really interested in, because this is the mounting point for the engine.
You said asshole?
Excuse me?
He probably misunderstood.
No, he's somebody who thinks he's really funny, saying curse words and making dumb jokes. So I get him out and block
Such
him.
a pussy. I'm sorry.
Yeah, I'll start blocking if somebody else starts disrupting the competition. And like one more thing, if somebody would do this a lot of times and permanently, there can be points deducted for unsportsmanship conduct, all the way up to being excluded from the whole competition. So yeah, like we'll be here for 2 more hours, so don't slow it down, please. Thanks. So back to what I was discussing. The mounting point is here at the top of the engine. These engines are mounted using M8 bolts. You basically have a bolt for this one in your engine mount bulkhead, and the engine is screwed on. So the insertion of the engine is really fast on the launch pad, which is good for the competition. Here is the thrust graph. You can also find this in the handbook. And now we can start with the main part, with the OpenRocket part. So I'll just change this. So what we will do today, and what is an OpenRocket? OpenRocket is software that's used for designing rockets, and not only for designing, but also for simulations, checking stability, and stuff like that. If you ever before worked with OpenRocket, this will be more like beginner introduction. So I won't have time to go really deep into explanations like about really do more advanced things like staging and stuff like that, because that's something that we don't really use in this competition because we have only one engine. So if you are here looking like if you're already pro in OpenRocket and looking for more pro tips and stuff like that, you sadly won't get that because we don't have time for that basically. But if you're completely new to this program, this is exactly for you. So this is what we will do today. We will design from nothing a whole rocket for this competition. But this is the result. How it looks for you when you open OpenRocket for the first time is like this. What you can see here, this is the rocket design part of this software, where here will be a tree with the components that we will make. Down here, there will be the rocket that we design. Up here are the components that we will be adding. But first things first, when we have this program, we need to import our engine file. I've sent it to a Discord with announcement of today's workshops, so you can find it there in the announcements. It's called Gragas, like the engine, and it's .eng file. So first you find this file and you download it. And then how do you import engine file into this software? We need to go here, second from the left, and down here you can find preferences. So we open this up. One more thing that I will just add, I have sadly here with me only one computer screen, so I can only present and I can't see if you're like trying to say something or writing something in chat. So if you have any questions, just ask them. And if you for some reason fall behind, or you like couldn't find something that I did here, and just ask me, because it's much better than for you to fall behind and not being able to follow this whole workshop. This workshop is also recorded, so if you want to just listen right now and then go through it later, there will be this possibility. So we opened this preferences window, and what can we see here? We can see here the interface language. I have it defaultly in English, and I suppose that most of you will as well, but there are a lot of other languages as well if you want to choose them. I recommend the English one because the whole software is done in English, so the translations can be sometimes a little bit weird. You can also choose a UI theme. That's one of the newer things. So you can choose a dark mode. I actually use the light mode because some things are just better in this software in light mode, but the dark mode can be really nice as well. But now to the engines. So how do you add your own engine? Defaultly, if you open it for the first time, here you will see only something like this one. This is where all of the trust cores of this software are stored. So either you find this file path and you add it to this trust cores you add it here. That's one thing. Or second thing, you can do same thing as me if you don't want to always trying to find this one because it's just buried. You can define your own path where you will store all of your engine files. So once you find this and you've put your file there, you can click on OK, and then you need to reset the software. The software does not recognize the new ones that you've put there before you reset it. So you just do that and reset the software. There are a lot of other like smaller settings, but these can be kept for now on default, all of them. I'll just ask: is there somebody who actually wants to follow this workshop right now with me? Because if there wouldn't, yeah, awesome. Yeah.
Yes.
Awesome. So I'll just give you a minute to just find this .eng file, to upload it, and to restart the software. And I'll just one more thing that I wanted to tell you that's new. You might have seen it on Discord as well. But if you want to use a ground station, we enabled the use of other different communication chips and frequencies. But be aware, we did not allow all of them. There are requirements that you need to meet. So just be aware of that. So now, hopefully, this went well. We'll find that out in a moment if you uploaded the file successfully. If not, we will find it out in like 5 minutes and you can try it again. But now, we are at the start. Well, how do you start designing a rocket? Well, you start by finding out the requirements that you have. What are the things that constrain you? What are the things that you want to have on board and stuff like that? So for this demonstration, I'll be part of a team that's for a second year in this competition. So we are in the advanced category. We decided that we want to do the ground station challenge. We don't want to mess around with roll control. And we want to do something special. We want to bring a GoPro as a payload so we can have really nice pictures and videos from the whole flight and get hopefully some more points for that in the design category. So that means, okay, we want to have GoPro on board. So I Googled GoPros and I found out that the newest one is 61 millimeters in diameter. It's 72 millimeters high and it weighs 154 grams. Then what are the other things that we just need to have on board? Well, we definitely need to have the engine. So I looked to the competition handbook, to the drawings, and find out, okay, the engine diameter is 43.4 millimeters. I know its length, I know its weight. Awesome. What else do we really need on board? Well, we need the altimeter because that's requirement. Okay, so I found out what's the size of the altimeter. I have that. We also want to have some onboard flight computer, some avionics. Here, it's just estimation, but for example, we estimated, okay, we'll need this flight computer and this chip for the ground station communication, and we want to measure this and this, and all together, it will be roughly like 100 bar 40 millimeters, 75 grams. This is just rough estimate. I advise at this point to make really conservative estimates. Just it's better to design it a little bit bigger and a little bit heavier and then scale down than the other way around. So those are the things that we really want to have in our rocket. What are the biggest constraints for us? Well, the biggest constraint for us is in terms of diameter of the rocket. So what's the smallest diameter that you can have? The smallest diameter, if we want to have a uniform one, is the 61 millimeters of the GoPro. And that's the inner diameter. So we want to have some thickness of the walls and stuff like that. So we can say, okay, our outside diameter will be 65 millimeters. You can also decide, okay, part will be 65, part can be smaller, but for the sake of simplicity, we'll just keep with the 65 millimeters. So we can start. In OpenRocket, easiest place to start is with the nose cone. So how do you work with this software? As you can see right here, I selected the sustainer. That's basically the first stage. You can also, if you double click it, you can rename it to first stage. It doesn't really matter. So I selected it, and now you can see I can select nose cone, body tube, and transition. I want to start with nose cone, so I click on that, and it opens up window. Every time, like most of your work in the OpenRocket will be done in windows similar to these ones. Up here, we always have a component name. It's a nose cone. We don't need any special name for it. So here we can leave it. There are possibilities to use parts from libraries. For example, if you would like to buy some parts, for example, nose cone from Estes or stuff like that. But most of the parts that are used in this competition are made in-house. So that's a possibility. If you would like to buy some parts, you can maybe find them here. But usually teams make their own parts. Here in the General tab, we can select the shape of the nose cone. For example, I've read some article and they said, oh, Hack series are the best ones for these rockets. So I'm just going to select that. Here we can play with shape parameters. This depends on the shape that you have here. We can edit the length. We can edit the base diameter. And now we set 65 millimeters. So I'll change that. I take a look at the nose cone. Yeah, 150 millimeters in length seems okay. I'll just leave it for now. And I select, okay, I want only 1 millimeter thickness. It's fine with me. So I change that. That's this part. Here we can select material. Defaultly always will be selected cardboard, but if you look at it, you can see that there's a lot of materials. So I, for example, want to 3D print this. And I would like to 3D print it from PLA. So I'm select PLA, but if you are following me, you maybe have a problem finding PLA. Why? Because it's not in the default library of materials. So how do you add something to that library? So you can also select it. I'll show it to you. If we go again to the preferences tab, so it's second from left. It's down here. So I open preferences. And here we started in the general tab and we move almost all the way to the right to the materials tab. So if I open that up, there are all of the materials that are in the library in this software. And you can see the ones that are a little bit highlighted are the ones that I already added. How do we add a material? Easy. We click on new. We write down the name. So we want to use PLA. Here are 3 options: bulk, surface, and line. Bulk is for components like physical, like this one, like nose cone, body tubes, and stuff like that. Bulkheads. Surface are for surfaces. For example, when you are making parachutes. And line, that's basically lines, like parachute lines and stuff like that. So we wanted bulk. We Google, we find, okay, PLA is 1.24 grams per cubic centimeter, and I would just click on okay, but I already have it, so I'll just cancel it. So that's how you add your own materials. I can actually see that in the new version, there's already PLA added in the software. I just find out. So maybe you don't need to do that for PLA, but maybe you want to use some other more interesting materials that you can't find here. So that's how you add them. So let's go back to the material. So we selected the component material. Component finish, I'll get back to that later. For now, we'll just leave it like this. There are also other tabs here. These three last ones are same basically for every component. There's comment, so you can write comments about this if you want to. There's appearance. This is, I'll mention it briefly in the end. In Photo Studio that this program has. So if you want to make the rocket nice in this software, you can, but we can leave it for now. It doesn't matter. In override, I'll also get to this way later, but this is used to override the parameters of the components because, as you can see, defaultly the software calculated that it should weigh 24.5 grams, but here you can override it and say, okay, it will be 50 grams. Software uses it as a 50-gram one, but I'll just turn that off right now. Here, the shoulder, that's a specific one for a nose cone. You can build the shoulder of it. That's used to, for example, insert it into a body tube. So you would be able to just do that, something like this. But I'll just turn it off because I did not prepare this part. Okay, we have our nose cone. Perfect. So let's continue. The next part that we will add is a body tube. And again, this will really quickly start to become the same, basically, all the time. Body tube, yeah, this name is fine, so we can keep it. Length, the default length here is 200 millimeters. At this point, we just estimate what do we think is good number. I know that 700 is good for us, so I'll just do that. One thing is if you leave this on automatic checked, it will always change the outer diameter according to the components, to the neighboring components. So if I would just jump out here and change the diameter of the nose cone, I'll make it huge so you can see the change, like 100 millimeters. You can see that the body tube changed as well. So I strongly advise you to keep this always checked at automatic. Here we can select either the inner diameter or the wall thickness. You can see if I change one, it recalculates the other one. So you can change just one of them. So wall thickness also 1 millimeter. I'll change the material. I'll change it to PLA, leave this. Okay, these three are still the same, but here we don't have shoulder, we have motor. So what's here? Here we can select if this component should be used as a place where the software can add the engine, where the engine can be mounted. For us, we want this, so I'll just check this and I'll leave the rest of this for now. So we have our body tube. We prepared it to insert engine, so we can do that. So we will head up here to the second tab, the motors and configuration. I'll select that one. It looks like this. On the left here, we have possible motor mounts. So you can see the body tube is there because we selected it. And here will be all those motor configurations. So we add a new one and window like this appears. For you, defaultly, it opens with selected all, with all of the manufacturers. So as you can see, the database is quite large, and you can find a lot of engines right here. There are possibilities how to filter everything and like that, but for you in this competition, the easiest way how to filter is to just clear all, and you should have a CRS, Czech Rocket Society, here as a manufacturer. So if you select that one, you will actually find not these many ones, because these are all of the engines that we worked with or tried to design or just did before. So you will have basically only this one. The Gragas V1 that you just download it and upload it to your OpenRocket. So you find this one. Here you can switch to show details. You can find details about the engine, what's the name, what's the total impulse, average thrust, burn time, launch mass, empty mass, the thrust cost, everything. Perfect. One more thing that's here necessary. This engine is defaultly locked. It does not have an ejection charge. So we found our engine. I click on OK, and now we have engine in our simulation. Everybody who's following me managed this step. Did you find the engine, or did anybody have a problem with that?
Yeah, I did.
Yep, all correct.
Awesome. So we can continue. At this point, if you would like to design, like you have only one engine to use in this competition, so you need only one. But if you would be trying to design a rocket and thinking about multiple different engines, here you can do multiple different configurations with different engines to easily compare them. So we'll head back to the rocket design. One thing that I did not show is this transition. As I said, for simplicity, we will use only one diameter. But if you want to like use a bigger diameter, for example, for the GoPro part, and then use a smaller one for the rest, you can use this, a transition. It works in a really similar way as the body tube, but you can change the diameter, not only the length and the fore diameter, but also the aft diameter. So you can basically make changes in diameter like this. So I would put this one, go from 65 to 40, and then I would do another body tube, and that's already defaultly 40. But I'll just delete this because we don't want it in our design. Now we will skip in the components all the way down here because we want to start adding things into our rocket, and we will actually start from the top. So what do you want up here? Well, we would like to have some form of recovery systems on board. Here are two options in OpenRocket, using parachute or using a streamer. Mostly in our competitions, team used parachutes, so we'll use that one. And we want the parachute somewhere where we want to split the rocket so it can get out and function properly. And one of the easiest places where to do this is just under the nose cone, where you can eject the nose cone and eject the parachute. So we'll start from top. We will start with parachute. So let's add parachute. Okay, parachute can be named parachute. That's fine. Here we can select the size of the canopy. For now, I don't really know how big it should be, so I'll just start by doing it 500 millimeters. We'll see. Maybe it will work, maybe not. Here we can select material. Again, that's the same. Here, this is the important part, direct coefficient of the parachute. The default one should be set to 0.8 in this software. The thing is, with parachutes, it's a little bit more complicated. I'll share on Discord a resource that I've used when I was designing rockets like this. So you can make different shapes that have far better drag coefficient than this 0.8. This is for the basic like sheet parachute. So be just careful with this, because it would be bummer to design a rocket around a parachute that you would say that has two, the coefficient as S2, and then you would try it and the real coefficient is way lower, and you would fall way too quickly. So just be careful with that. Down here we can change the number of lines and how the lengths are long. I'll just keep this for now like this. Here we can select the placement of this component inside this rocket. You have multiple options. We can do this from tip of the rocket, from top of the parent component, which is the body tube, from middle of it, or from bottom. Usually, the easiest way how to work with this is if we are closer to the top, I use the top of the parent component. If I'm closer to the bottom, for example, like the engine, I would use the bottom. Here, we can basically change on this scale where is it supposed to be. We want to have it up here, so I'll just keep it at 0. If OpenRocket added in like few versions back, added options to automatically calculate the size of this parachute. The thing is, if I click on this automatic to calculate it, it calculates it like this: bucket diameter 63 millimeters, bucket length 4 millimeters. This is theoretically right, like in terms of how densely you can pack the parachute, but this is not how it works in reality. So just be aware of that I'll probably keep it to at least 20 millimeters, but probably it will be a little bit more because it's not that easy to pack a parachute correctly. But I'll just keep it for now at 20 millimeters. Here, regarding the deployment, we'll get to that later as well, but I can already change it here, because here it says it deploys at first ejection charge of this stage. As I said, our engine does not have ejection charge, so in the simulation this would never open. So I'll just change it that it opens at apogee plus 1 second, because it takes us a little bit of time before we detect the apogee and before the parachute is ejected. There are also different options here. We can open it at a certain time after launch, or we can, for example, open it at specific altitude during descent. This is mainly used if you have 2-stage parachutes, a drogue one and big main one. So the main ones are usually set to open at specific altitude during descent. For the inner components, you can set a radial position. It can be offset from the middle, but usually you don't need really this option. The same is for radial direction. You can spin it. Okay, we have our parachute inside. So what else do we need? Well, we need, or we would like to have a shock cord to connect the parachute to the rocket. So the shock of opening of the parachute is at least somehow mitigated. We have that here as well. So we can add a shock cord. Here I will not change many things. I can leave this at the default. Yeah, in your design, you will change this, but for the simplicity here now, I don't need to change the material. And I'll just move it. I'll just move it 20 millimeters down. I also can for now leave this as it is. Okay, so we have a shock cord. Now we need somewhere to attach it. First, what we attach it to is a parachute yoke. So how do we add a parachute yoke? Well, we use this last one that we have here. That's a mass component. So if I open that one up here, you can find a mass type. This actually only thing this changes is the appearance. If I move this to the side, you can see that if I change this appearance, you have different icon here. So this is basically good for being able to orient yourself in this program to clearly see what's what. So we can choose it's a recovery hardware. The parachute yoke, for example, weighs 50 grams. Again, for the simplicity, I will not change the size. We can add it under the shock cord. Okay. Again, radial position and all of this, it's still the same. And here I will finally start changing the component names, and I will change this name to parachute yoke. Okay, cool. So we have that one, but it's still floating inside the rocket. How is it attached? Well, usually it's attached using some form of bulkhead. So we can do that. We can make ourselves a parachute bulkhead. Bulkheads are up here in the inner components. In this example, we will be using only these two types, the bulkhead and the center ring. Short note to the other ones, inner tube is usually used if you want to have a cluster of tubes inside, and it's the easiest way how to make a multi-engine rocket in this software, because basically you select, okay, I want to have 6 in this configuration, and I want this to be a rocket mount, and then you can add engines to each one of these tubes. So it's mainly used for having multiple engines. We don't have that. So how it goes. Tube coupler, this is used if you want to connect two tubes together. Again, basically select outer diameter, inner diameter, stuff like that. And engine block, this is basically a fancy type of bulkhead that can be used for engines, but I actually never really used it because the bulkhead component does basically the same for me. So let's select the bulkhead. Again, we can select thickness. Okay, it's a parachute one. It should be quite sturdy, withstand some loads. So I'll make it 10 millimeters. I'll keep the diameter. As you can see here, it defaultly selected position from bottom. I want to have it up top, so I'll do it from top. And I'll just slide it down here. Here, of course, the easiest way how to do this is like correctly, exactly, is to calculate. Okay, I know the length of this, length of this, length of this. I'll add it. That's it. But here I'll just do it quickly. So I'll just shift those. I can change the material. And yeah, awesome. I have one thing I forgot. I always forget about this. I can change the name because we will have a lot of bulkheads. So we want to name them so we can find out which one is one. So this is a parachute bulkhead. Here from here now, I will a little bit speed up because we want to have the GoPro there, we want to have the avionics there, we want to have the altimeter there, but adding these new mass components and these new bulkheads is the same thing again, and again. So if you are following, if you don't have one of those there, it doesn't matter. But for the sake of our time, I'll just do this one quickly. So I'll start with the GoPro. Why do I start with a GoPro? Well, we'll get to a stability later, but basically what you want to achieve, you want to have your center of pressure as low as possible and center of gravity as high as possible. So it's always good to mount the heaviest things close to the top as possible. So from the 3 components that are left, GoPro, avionics, and altimeter, the heaviest one is GoPro, then it's avionics, then altimeter. So I'll start with a GoPro. I'll add mass component, rename it. For us, this is payload, so I'll set it up. It's 154 grams. The length is 72 millimeters. The diameter is 61. and I'll shift it. I'll shift it down here. 80. Awesome. We have it there. Okay. Then we want to do parachute, the bulkhead for that. For simplicity, I can just duplicate things here. So I'll duplicate this bulkhead. I'll rename it. It's GoPro bulkhead. It does not need to be that strong, so I'll just change the thickness, and I will just shift it. If the changes are not applied immediately, you just click somewhere else, or you press Enter, and the changes apply. Okay, we have our bulkhead there. Then we continue. We make the avionics. It's again the same mass component. We name it. We change the mass type, so it's nice. It's a flight computer. We think it's 75 grams. Length 100. Diameter 40. And we move it. And again, this process repeats a few times right now. Okay, we have our avionics bulkhead, and the altimeter will just hang basically from that one. So we'll add that one, and it will be the last one in this category. So our altimeter weighs only 13 grams. It's 61 here, 36 here. Let's move it. And awesome. Okay, so we right now added all of the components that we want to add, but we're still missing some bulkheads because as you can see, our engine right now is just levitating. So first I need to add a parachute bulkhead. So I'll duplicate the motor mount bulkhead. So again, quickest way, I'll duplicate the parachute one, edit it. It's engine one. It's close to the bottom. So actually the best way how to do it is have it from the bottom. Why? Because if I would have this, if I leave it like this, and I change the length of the body tube, okay, I needed to make it 800 millimeters. You can see basically we have a free space in the middle right now, but the bulkheads, all of them stayed where I want them. But if I would do this not from the bottom, but from the top of the parent component, and I would change the length, you can see it moved somewhere where I don't want it. So that's why if the bulkhead is should not move relative to the bottom, I do it from the bottom of the parent component. Okay, we have engine bulkhead, and we want to add one centering at the back for the engine so it can't wiggle. It's secured in the axial direction. Here, the one change with the centering to the bulkhead is that you have this inner diameter. So that's 44 millimeters for us. Leave the position. We can again just change the material, and okay, it's done. It's there. So these are all of those inner components. So what are we missing? Well, the really obvious thing that we are missing are fins, because we want need to have this rocket passively stabilized. We don't have complete stabilization using something like thrust vectoring. So we want to add fins. There are 4 options how to add fins in OpenRocket. You can see them, all of them here. There are trapezoidal ones, elliptical ones, freeform fins, and tube fins. In this example, I'll be using the trapezoidal ones because that's the easiest ones of them together with the elliptical ones to work with them. But if you want to try to do something a little more like experimental or like I would say complicated shapes, you can try the freeform ones. It's actually really fun to try to do that, but it takes longer to perfect the shape. So I'll just stick with the trapezoidal ones for this design. So, and again, back to windows and selecting everything inside of them. We start with the number of fins. I want to use more of smaller ones, so I'll just use 4 fins. They are also easier for us to mount. Fin count, you want to leave this at 0 because you don't want the rocket spinning excessively. And now the root chord is this length. The tip chord is the length on the tip. Height, that's kind of obvious how high the fin is. Sweep length, and sweep angle, how swept to the back it is. At this point, you would start editing this, trying to find out what are the numbers that you want. And usually when you do this, you look up here where there's stability specified. I'll just, because we don't want to be here way too long, I'll just do the numbers that I want that I know that we want, and I'll just explain it afterwards. So I'll be using root chord of 100 millimeters, tip chord of 70, height of 68 millimeters, and sweep angle of 24. Okay, just to finish the fins before we get to the stability. Fin cross section, there are 3 options: square, rounded ones, and airfoil ones. For example, I say, okay, we won't be printing them. I'll use just the rounded version, and they will be really thick, just to make sure that they don't break. Okay, 4 millimeters. Again, here you can specify the placement. It doesn't constrain you anyway, so like this is possible in regarding to the software, but it's not possible in reality. So just be careful with that. But it can help you, for example, to shift them just a little bit if you need a little bit more of stability. But I'll just keep it at 0. Material, again, you select something that you want to use for this. For example, or in my case, I'll be using PLA as everywhere else. And here, now I will explain the component finish, actually. Because as you can see, what's a component finish? Where you specify the surface. Here, the default option is always regular paint at 60 micron meters. What does it do basically for you? If you can, if you look at this window up here, you can find the actual the stability that you have right now. To the left here, you can find the length, the diameter, the mass, width, and without motor. And down here, you can find the apogee that you have right now, the maximum velocity, and maximum acceleration. And as you can see, if I reduce this, for example, to a mirror surface, it's a little bit better. And if I would do set it for all, this would change the component finish for all of the parts. We went from 500 meters to 533. This is awesome, right? Well, yes and no, because you will have better apogee, but you are never achieving this. So I actually strongly advise to, at the start, stick with the regular paint. because if you do just a regular finish of a rocket, it actually works really well. And then if you want to have something more fancy, you do really good painting, or you are creating better surface for 3D printed parts with acetone, you can go lower here, but just be careful with that, that you are realistic, because yeah, like nice numbers are awesome, but one of the categories that we are competing in is accuracy of prediction. So you want to have accurate predictions. Here you can do fin tabs. Those are the small mounting points. If I would do them here, you can see them. But in this design, I'll just keep this at 0. Here are small last options. You can split them or you can convert them to the freeform ones, but I'll just keep it this way. Okay, awesome. So now we are almost finished in this window. Almost, because the last thing that we are missing are the rail guides, the guides that keep us in our launch rail. For this, there are two options: rail button and launch lock. In our composition, we are using launch rail, so we will be using this one. Did anybody? I heard something. Did anybody have any question? Okay, I guess everything is fine. I'll just go quickly through this because I did my work before, so I found out how big of these rail buttons we need. So I'll just quickly change this outer diameter to 10, inner to 8, the total height to 10, base height is 2, and flange height is 5. This roughly corresponds to the ones that you will be using. And we want to have 2 rail guides. Here the separation should be something like this, if I did everything correctly. And I'll just move these components. I almost did it right. I'll add the position to the top of the rocket. Yeah, good enough for now, because the best place where to put the rail guides is into the big bulkheads that we already have, because they are structural strong points. Again, I can change a material, I can change finish. Okay, cool. So we finished this one, and we'll be heading to the simulations. Anybody have any questions, or do you need a little bit more time? Is everything fine?
Yes.
Awesome. So I'll just quickly step over this one. Here we already did the engine configurations. Right now, because we added a recovery device, the parachute, this part actually is finally clickable. So here you can easily do different configurations also for the recovery system. So if you would like to have okay, we will have 2 configurations with the same engine, but one of them can have a parachute at apogee plus 1 second, and one can, for example, have apogee plus 2, and we can compare those. So that's an example how you can use this. I'll just delete the second one for now. So now we are getting to the flight simulations. Here you will have your first, or the program should make the first simulation for you. What you can see here, a lot of things, but we need to start with something else. And actually, we'll start that up here again in the Preferences tab. So we'll head there through Edit and Preferences. And here you can find a tab Simulation and tab Launch. These ones are useful, especially if you are working a lot in the OpenRocket and creating a lot of new rocket designs and stuff like that. And you have uniform places from where you launch, and you have uniform launching platforms. Because here you can change the parameters of the simulations throughout the whole OpenRocket. The important thing is here in red that this will not change in the simulations that you already created. This is for the new ones that you will create. So just keep that in mind. Here in the simulations, I usually use as small step as possible, because we have like our computers are powerful enough to calculate everything quickly, even with small time steps. And here in the launch, I always leave. Somebody should mute themselves. I don't know who that is, but just keep that in mind, because we hear random sounds from time to
I
time.
think they're trolling. They mute themselves. And
Yeah.
Like, I heard Victor said something.
Just please, everybody, mute yourself if you don't have any questions. And like, if you will not be muted and you will produce different sounds, you will just be kicked. So the wind speed, I always keep it the same. But for example, on the launch day, if the weather is really, really nice and the average wind speed is only 1 meters per second, I can change that, and I can do the simulations again and have far more accurate simulation for the exact launch day that we have. Same here is for the atmospheric conditions. Best thing is you leave this defaultly as using international standard atmosphere, because it's actually kind of easy to make mistake. And I've seen one occasion where we forgot, we put in the wrong number for pressure, and the rocket simulation was basically in a vacuum, and we were wondering why we are flying 2 times as high. Same here for the launch site. This launch site I have set up as the one in Brno that we will be using. And the important part in this window is the length of here. You need to set up the length of the launch rod. In our case, it's 2.5 meters. So just set it up because it will be really useful and basically necessary. Okay. So we've prepared this for the next time we are doing new concepts and stuff like that. But now let's look at the simulation in this file. Right here, you can see all of the really important things from the simulation. We can see what's the velocity from the launching rod, what's the apogee, what's velocity at deployment of the recovery system, optimal delay, maximum velocity, maximum acceleration, yada, yada, yada. If I click at this one, first thing I will check, and I think it will be wrong in this one, I'll just check the edit simulation. The same window opens, and as you can see, this is the previous length that I used in the software. And because I did not reset it, it's there again. So it's 2,500 millimeters. And so I changed it right now only for this simulation. And I don't need to change anything else. Everything else is fine. So I'll do simulate and plot. As you can see, the simulation was really quick. And now it opens this plot/export window. How do I open it up if I want to open that like from scratch? It's here. So You open the plot export. And what can we see here? Well, in this plot data tab, you can first choose one of the standard plot configurations. There's quite a lot of them. The default one is vertical motion versus time, and we'll start in that one. You can change basically everything here. You can change the x-axis type to a lot of parameters that OpenRocket produces, but we'll keep that at time. Same thing is here, we can change what we can see on the y-axis. We can delete some of them, or we can add more. Like, for example, if you would like to know the mass of the rocket at the point, we can keep it here. Then we don't want it, so we just delete it. Up here are important flight events, like launch, apogee, ground hit, and stuff like that. I'll also check the launch rod clearance because we want to check that out. And now we just hit a plot, and we have our graph. So what we can see in this graph, we can see what we selected. So altitude, vertical acceleration, vertical velocity. Yeah, one last warning for the one who just doesn't know how to mute himself. If that person does it again, please just tell me who it is and he'll be gone. And I'll ask that from a captain of the Polish team, because I know you're not the one doing it. Okay. What we can see here, yeah, that's the simulation. You can easily zoom this in either using these or using your mouse. For example, if we want to check, okay, what's our acceleration when we are leaving the launch rod? What's our speed at that point? You can, if you need to find out some information, you can just check it here. One thing that we, for example, want to check out is our vertical velocity while we are falling on the parachute. So we can just look at it more closely. Is this line? Yeah, that looks a little bit high. Well, yeah, that's high. How high is it? One pro tip here, it's really hard to find a point where we can like where it shows us. I found it right now, but I was searching for a long time. So if you want to search for these points, you click down here to show data points. And yeah, here it displays, here it doesn't. Here it displays, here it doesn't. But if you leave this on, it looks like this, which isn't nice. So I have this defaultly off, but if you want to find the point, yeah, you do it like this. So the velocity on the parachute is a little bit high. So we go back to our design and we change that. We change the diameter. So let's say 500 millimeters. That should be enough. Let's go back to simulation. Let's run it. So, and you can see already here, this thing you can actually find out here. What's the ground hit velocity? And it's 7 meters per second. That's perfectly within parameters because rules specified it should be between 5 and 9 meters per second. That's almost in the middle. Perfect.
Marco.
Yeah. Okay. One more thing that we really want to see in the simulation right now, because like, yeah, you can find a lot of really interesting things there. But the one thing that we really want to see right now is the stability versus time. Because for this year, we actually changed the rules regarding stability. We got away from having one stability number that's just required at all points to changing the rule to being that you need to have at least one caliber of stability before you leave your the launch rod, or like at the point of leaving the launch rod, you need to have at least one caliber. For those ones who don't know what I'm talking about, what are calibers, how do you measure this stability and stuff like that. Rockets are passively stable when your center of gravity is closer to the top of the rocket than your center of pressure. Center of pressure is where all of the aerodynamic forces act. Center of gravity where the mass acts. Said really quickly. What are the calibers? Well, caliber is the diameter of the rocket. So if we have stability of 1.92 right here at Mach 0.1, that means that at this speed, the distance between center of gravity and center of pressure is 1.92 times the diameter, 65. We want this stability to be always at least once when we are flying to the apogee. Why? Because if it's lower, the rocket is not stable enough. We don't want this to be also like really, really high, like having stability something like 6. That's way, way too much. So if you balance it, that you have a little bit above 1 caliber when you are leaving the launch rod, it's perfectly fine from our experience throughout the whole flight, because the stability changes, as you will see right now. The stability changes through the flight. It's because of the effect of the speed and effect of burning the fuel. So when you burn the fuel, the center of gravity shifts forward, so you are more stable. And as you can see, actually at this point, we managed to already find a good enough stability, just barely. It's 1.02. I actually had it prepared, so it should have been like 0.9, but we made something different. So we passed it right away. And as you can see, the highest stability reached is something about around 2.7, which is perfectly fine. So that's the one thing. If we would not make this, you can go back again, and either you can change the stabilizers, you can move components inside, you can add additional weight, for example, to the nose cone to balance it better, and stuff like that. So those are the main things. There are things that I skipped, and I'll just go quickly over them and explain why. First thing I did not explain are these assembly components. As you can see, we work only with the first stage. We are not staging in this competition because you have only one engine available. But if you would like to make a 2-stage rocket, you would just add second stage here. The same thing goes for boosters and for pods. If you would like to see some example of these, here in the file section, you can find open example. And here you can actually find examples of different rockets, 2-stage rocket, 3-stage rocket, air start timing, and really interesting things that can be done in the OpenRocket. So if you want to check that further, you can just open that one and take a look at it, how it works, how the simulation works with all of these engines, how it's configured right here, and everything. So you can check that out. Then there are also different tools that you can use in this software. They are here under the tab named Tools. The first one is component analysis. This enables you to see more clearly what are parameters of different components, what are their direct characteristics, what are their raw dynamics, and this you can change based on the Mach number, roll rate, and everything. So that's for this window. The second one is rocket optimization. This is actually really interesting. Here, for example, you want to check the like you want to try to optimize some parameter. Okay, you want to change, for example, we need, I'll do just a quick example. We have some mass in the at the start of the rocket because we wanted even higher stability for some reason. So I just added this one, but like, yeah, balancing where it should be, how heavy it should be. Yeah, it's always, I need to change it, then look, okay, this is not good, and stuff like that. So the software can do this for us. So if I open the rocket optimization, I find the mass component, I click this, and I can change the mass and the position. I add them. These are the current ones. These are the limiting factors. So yeah, minimum 5, maximum 60 grams. Here are the positions. And here I want to change, okay, minimal stability that I want to achieve is 2. I want to optimize this for apogee altitude, but yeah, you can optimize for a lot of parameters like maximum velocity, acceleration, everything. And I want to maximize that value. And I'll start optimization, and it basically does all of that work for me. And it finds out, okay, the best thing would be to have 40.3 grams at 3.87 millimeters. And I can apply this optimization. And as you can see, it was applied and did its job. So that's the rocket optimization. Just be careful with that. You need to carefully restrain the optimization because, for example, if you are trying to optimize the shape of the fins, if you don't constrain it correctly, basically the first thing it finds out is that this is the best stability that you can have. And like, yeah, the software is not wrong, but you will never manufacture this, of course, so be just careful with that. Then this one, I'll just skip. Like it's really way more advanced, and I actually never really got to learn this part, so that's why. And the last part is a photo studio. If you want to make a render of your rocket, a simple one, you can play around with it here. You can change the environment. So we can have, for example, frozen lake and yeah, have stuff like that. We can change the orientation of the rocket. So yeah, and stuff like that. So if you play really carefully with this, you can end up aiming at somebody on the picture. But yeah, this is completely up to you to just find out what you can do. But if you would like for the rocket to look differently, then we get back to the window of appearance, where here you can change the texture, the color, and everything about that. One last thing, I, for example, for some reason skipped it the last workshop as well. One thing that you would like to do, because yeah, now you designed it, it looks good. So you do your CAD designs. What you can do actually, for example, if you want to have this nose cone, they added this in like this or the last version that you can export these parts in that OBJ in an object form. So you can actually export that. For example, for the nose cone, how do you do it? You need to have the part that you want to export selected. So nose cone, it's selected. Now in File, Export As, it's possible. So you built everything, and now you want to find out if the simulation will perform correctly. Well, the program here, if I, for example, open up the body cube, the program here thinks that this component has 175 grams. But you manufacture it and you realize, oh no, it has only 160 grams. Well, you go, as I actually showed previously, you go to the override, you click on this, you can override the mass, and you can change it. Same thing goes for changing the center of gravity, changing center of or coefficient of the rack. One more thing is you can here override it for all subcomponents. Subcomponents are the ones that are below this component in the component tree. So you would, for example, want to use that if you want to, if you actually measure the center of gravity of the whole rocket once you manufacture it. And this is actually, so you override it not only for the first stage far, but for all the subcomponents. You say, okay, we measured it, it's here. So yeah. And actually the thing is, as you can see here, if I change the flight configuration with no motors, then it's when this is the same. So that's good because you don't have back at your workshop our engine. So you measure back at your workshop when you have everything like this assembled. Okay, it's 300 millimeters. So you add it, you turn on the engine. Okay, the stability is way nice. Awesome. I'll just turn it off. And that's basically it. I've tried to make it faster than before, but it's still like more than an hour. Do you have any questions?
No.
Also, no, everything was pretty clear.
Awesome. Yeah, that what happens when I say it 2 times in a row. Second time it's much better.
It's about training.
yeah, basically. Yeah, like one more thing that I want to add is like the OpenRocket is recommended software to use because we know it's good, it's reliable, it's free, it's easy to learn, it looks nice, it's easy to learn. I said that one already, but it's not the only one that we allow. I can't tell the names from the top of my head for the different ones, but I know, for example, that Euroc specifies use of different software. So if you would want to check the stability in that one, sure, not a problem with us. But and like if you want to use different software or your own, for example, for calculating the apogee and everything, yeah, we don't have a problem with that. The only thing that we really need to have reliably from you is the center of pressure, so we can check the stability with you that it's all right before you launch. So yeah, if you don't want to use OpenRocket, you don't have to. Maybe should have said this at the start.
Okay, that's good. So I have a question because I don't think that I understood it properly. It's not connected with OpenRocket, but
Okay.
with this LoRa
Okay,
module.
sure.
So is there a possibility to use a different producent or?
Yeah, but we specified that you can't use 2.4 gigahertz because sadly we have already things for our communication and especially for stream, and we are not now at the point that we can't change it for this year. So you can't use 2.4 gigahertz, and there's also a bandwidth. It's in Discord. I'll just don't know that one from head, but that's the bandwidth that our radios use. This one, so you can't use this one as well because we need to have radios for communication. So these are the frequencies that you can't use, and you need to be compatible with the addressing of those messages. So you can just into the message that you send, you need to incorporate address that will be given to your team. So we like everybody who receives the data can distinguish between data of one team and different team. So yeah, so like you can both transmit at the same time, but it's distinguishable which data package belongs to which team.
Okay, that's clear. That's clear.
Yeah. Like our objective will obviously be to try to separate the teams with ground stations and with the same frequencies to different launch windows. But the thing is, it might not be just possible because we are launching 3 teams at once, or in really quick successions. We have 3 launch ramps, 3 teams prepare there. Everybody leaves. 1 is fired, 2nd, 3rd. So yeah, like all of those 3 will be turned on at the same time, and yeah, like with the amount of ground station teams, it might end up with 2 of the same frequencies launching at the same time. So yeah.
I have a question about the launch ramp.
Okay, sure.
So here in the rule book, it only says that it will be 2.5 meters long,
Yeah.
but also here on the photo, you can see that it's not actually pointing straight up, but it's tilted slightly. And I have a question: is this something that we will be able to control, or is it just set by the organizers?
It's set by the organizers. There was actually in the Czech part last week, there was also a question about this. It's actually set by the organizers. It's because sadly we are launching at a place that quite restricts us in some ways, like where we can point it and where we can safely land. So we always try to keep it as straight as possible, and the direction usually never changes through the day because that's more complicated. But if the wind changes, especially in intensity, it might be that at the start of the day, it's, for example, 2 degrees, and then we need to tilt it more to 3.5, for example. You will be given the angle of it before you go launching and before you need to announce the expected altitude. So like the expected altitude you announce only when you are basically going for launch. So that means that up to the last point you can check the weather, the wind speed, what's the angle of the launch ramp and everything. And the launch ramp will be the same one, but the launch rail will be a little bit longer because the one from the last year was 2 meters, but we prolonged it to 2.5 meters for this year.
Okay, thank you.
Yeah, one thing I'll publish, or we will publish English new English version as well. But yeah, we just finished everything today regarding the Czech version, checking everything like that, and we did not have managed to translate it yet. We will do it as soon as possible. And like the only things that changed were regarding the stability. We specified that 1 caliber at leaving the launch ramp. I clarified the ground station, so you already can find basically the same thing on the Discord, and we changed the engine for the engine that we will be actually using. So those are the only changes in this new version. I should not have closed that.
May I have a question?
Also, yeah, sure.
I'm speaking for the Polish team.
Yeah.
And we're planning to use a prism as the top of the rocket. Do you think that it's good for the aerodynamics?
Using what?
A prism that's like a cube that has two longer sides, two longer sides.
Okay.
Basically, bigger cube.
Like you're basically using a different like nose cone shape. That's none of these, right?
It's like Hrano.
Yeah,
in
yeah.
Czech.
Okay. Why?
We think it's good for the aerodynamics.
Okay, sure. Like if you can justify it in your report, and if the stability will be okay, it will be a little bit harder to like prove the stability, because like yeah, basically in that case, OpenRocket does not know this shape. It won't. You can't select it. So we might want to see for you, from example, like yeah, why you think that the stability is enough of your rocket using this type of nose cone or like nose cube.
Okay, thank you.
Yeah. Interesting. I never seen a rocket in this configuration actually fly. So like, we'll see. So if that's all of the questions, where can you find the Discord link? We send it to the emails that you used for signing up for the competition. So you should have received email with Discord links. If you did not receive that one, check with your team captain if they received it, because they should be the ones who put their email there. And if they don't have it, just write us an email. You can find the email on our website and just write us email. Yeah, we would like to receive a new Discord link, and we'll send it to you. So to just quickly close it up, yeah, as I said, the next workshop is meant to be a workshop with teams from last seasons, where they will talk about their experiences in our competition and like give tips and tricks, what they did and what they fucked up, everything like that. As I said, I'll try to ask them if they will do English version as well, but I can't guarantee it at this point, sadly. So I'll just let you know. But yeah, that's basically it. Sadly, I can't do that one because it's been like 3 years since I took part in this competition, and we like really fucked up. So yeah, you would not learn much from that. And yeah, that's everything for today. So if you have any other questions.
I don't have any.
I just spoke with our team captain and we agreed on the prism as the top of the rocket.
Okay, cool. I'll be really looking forward to seeing the design.
Pavel Babowski said that it's a good idea.
We'll see. Yeah, like I'm not discouraging you from like anything. Like that's the one interesting part of this competition, seeing what like teams think of and how they approach the challenge, basically. So yeah.
So thank you for your time. I
Yeah.
think that we haven't got any questions.
Okay, sure.
Everything was clear, and thank you for your time.
Yeah, it's been my pleasure. I'll stop the recording right now. Yeah, this time the recording finally worked. Last time it was a little bit sketchy, so I didn't record the English part, but today I recorded it. So as with the Czech part, we will upload it once it's it's finished by Google.